Hello, hackers. Welcome to the Pwn Day 1 workshop. And so to give a bit of an introduction, uh, these are the trainers for today. So we have Howei, he's from Hwa my name is Nicola. I'm from ACJC. And the third and final trainer is Zhihong, who's from Raffles Institution. So across these 2 days, you're going to be learning how to exploit binaries in 2 different parts of the, the the memory regions. Right. For the first day, we're going to be covering some prerequisites, stuff you should know about before we actually begin real exploitation on the stack, which is a memory region inside the binary. And on the second day, we will be teaching you guys how to exploit vulnerabilities related to the heap, which is a separate memory region. Right. So first of all, for those who are new here, what is binary exploitation? Well, binary exploitation is about being able to exploit certain vulnerabilities or logical flaws, assumptions that the programmers make about their program, and using these kinds of wrong assumptions to make it do things that it normally shouldn't be able to do, right? So some examples you would have seen in daily life could be something like video game cheats. Sometimes you might see on the news about hackers who run code on a remote server and unauthorized access to files and permissions, or being able to leak privileged information in memory. So, for example, you might have seen before people who are able to run custom apps on their Nintendo Wii, which is basically done by exploiting certain vulnerabilities already present in the Nintendo operating system. Right. Another example would be Counter-Strike through wall hacks. So for those who are in the FPS community, you might have seen these around, which are like hack clients that allow you to do things in-game that normal players shouldn't be able to do so. A third one is the exploit that we showed you on the opening ceremony day, when Lucas showed you guys how to gain an example of gaining root privilege in a Linux system when you're a user with normal rights. And this is usually done so by exploiting vulnerabilities in the kernel. So those are some examples of binary exploitation. But in general, the main goals are usually to be able to read, write, or execute things that we shouldn't be able to execute. Right. By using a combination of any of these three, what we call primitives, we can basically solve any binary exploitation challenge or exploit any piece of software. Okay, so first of all, we're gonna go through, before we do any real exploitation, we're gonna be going through some prerequisites like how these executables or programs work in the computer, right? And first, to do that, we need to understand the ELF and memory layout. So first of all, when you think about programs, you think about these kinds of files that contain instructions for the computer to execute, right? An example of this you might be familiar with are exe files in the Windows system, which is when you, let's say, install an app, you might see that it comes with an exe file. And if you double click on this file, it will run in your terminal, or even just run the application itself, or maybe set up an installer to install the actual application. So these are actually files that contain instructions for the computer. You can kind of think of it as cooking recipes, right? So for a cooking recipe, you might have these instructions step by step. For example, over here you can see first we have to heat the oven to a certain temperature. We have to cook the baking dish with a certain spray. and then there are more and more steps after each one, and eventually you get to the end result, which is to produce this perfect dish that you're trying to make. So in essence, programs are exactly like this. They are basically recipes for the computer. So by nature, these things, these are files, right? These programs, and the instructions, instead of being as being human readable plain text, they're stored as these bytes in memory, right? So the thing is, how can we access these instructions, or how does the computer know where to access these instructions? So this is where we have to use the concept of an address. An address is basically a certain number that the computer assigns to parts of the memory, right? It allows the computer to know where something is exactly and allows it to access that piece of data at a specific location, right? You can kind of think of it as your house address. When you live in Singapore, for example, your HDB flat might go by a certain address. That address would tell officials or people reading it which part of Singapore you're in, which apartment in that area that you're in, and also which exact flat in that apartment block that you're in, right? And these are basically addresses. They allow the computer to index uh, parts of the memory, specific parts, using assigned numbers, right? Now, the way this works is that for each address that you get, which is usually a number that is incremented one by one by one, each number is assigned to one byte in memory, right? And by saving our program instructions, which were bytes, to memory, we can access the instruction by specifying the exact address that we started at. And by incrementing or decrementing the address, the computer can access specific parts of the program or specific instructions. Now, another thing that you might see in this subject is the concept of an ELF. So, an ELF is basically the executable and linkable format. In essence, it's the exe file, but for Linux, right? It specifies how and where these instructions are stored in memory. And the way it does this is by using addresses when it's loaded into the kernel, right? The ELF specify a kind of memory layout where specific types of data are stored, and they're stored differently, right? For example, over here, there's a specific region dedicated to storing the instructions, right? When you run an ELF. But in other parts of the memory, they might be used for other things such as user allocations, right? So maybe when the app is parsing something at runtime, it might want to parse that data and save it in some other region. But we wouldn't want it to be inside the region where we store the instructions. So they're gonna use another kind of region, let's say the data, the .data.pss, the heap, and you'll just save it there, right? So there's this distinction between a region for instructions and a region for generic data. Now over here, there's another special kind of region, which is the stack. Now this is something that we will go through later on, but the stack is going to be used by the computer for basically data that is kind of temporary. So some things, as we will see later on, could be the function context, right? When you enter specific functions and you exit this function, data that is specific to that function call will be stored on the stack, right? So yeah, dot text specifically will be storing the instructions. .data and .bss will be storing uh, the certain global variables in the program. So for example, coming over here to uh, let's say we were writing a C program, right? If when you write a function and you're initializing a string such as this string, the program has to know where to store it so that when we reach that part of the function, we can reference the string. Now, this string would be stored in the .data or .bss region, right? And the difference between .data and .bss is that, as you will see later, there are different permissions associated with each of these regions. For example, .data will be a read-only kind of region. For example, these strings, the program or the compiler knows that these strings will not be changed at all, right? They won't be modified or written to. So it's gonna store it in the .data section because it's not writable, right? On the other hand, if we have something like a global variable, maybe something like int, a count variable that we know is going to be incremented per function call. Like let's say over here, we every time we call this hello function, it's going to increment this count variable. Then the compiler would know to store this inside the .bss because the BSS region is writable, and since it's writable, we can increment the count. Yeah. Now another memory region, a kind of memory region that we will go through later on in day 2 more specifically, is the heap. And what this memory region is it's a bunch of space that's used for dynamic data allocation. So what that means basically is that let's say let's say you were on a run, like a kind of grocery run, right? Or maybe you're shopping. Let's say you're shopping. You don't know exactly what you're gonna buy, right? You don't know how big the item that you're gonna buy is gonna be, right? So to do that, you're gonna bring some sort of very big bag. And whenever you want to keep the item that you just bought, you're just gonna put it in the bag, right? And hopefully it will fit in the bag. Well, the heap is sort of like this. It's a space that grows and shrinks as the program requests memory or it frees memory at runtime, right? Now, the exact mechanics of this is something that we're gonna be elaborating on more in day 2. So don't have to worry about this right now, but at a glance, yeah. Now the stack is the important memory region that we will be focusing on because the stack is used for managing function calls and local variables. So if we go over here again, let's say I have some local variable, um, this count2 variable. Now we know that this global variable, the count variable, is going to be stored in the BSS. But instead of storing this local variable in the BSS, the compiler is going to store it in the stack. And the reason it does this is because, well, it's a local variable. Only this function should be able to use this variable. So each time there is a function call, this piece of data is actually temporary, right? And this is basically what the stack is used for. Now, as local variables are scoped and declared, the stack itself also grows on strings, right? And one important note about it is that the stack grows from a higher memory address to a lower memory address. So the, the exact meaning of this, I'm not going to elaborate it for now, but yeah, this is just something to note. Okay, so what exactly did we mean by high to low, right? That means that as you go to the top of the stack, the memory address from the bottom of the stack to the top of the stack actually decreases, right? So if I were to draw a diagram over here, let's say that we have some sort of stack. Okay. In the physical sense, this would be something like, you know, some sort of tower, let's say. So for those of you who might have heard it before, something like the Tower of Hanoi, right? And the Tunnel of Hanoi is this game where players would have to stack like different colored uh, rings onto a tower like this, right? And if you look at this carefully, right, you will notice that let's say you push in the blue ring first, right, and you push in the green ring and you push in the yellow ring, and you push them in this order: blue, green, yellow, orange, red. You're gonna see that the red one is always at the top of the stack, right? This is called pushing, right? When you push to a stack, it goes to the top of the stack over here, like in this Tower of Hanoi example. Now, in the computer, if we use this visualization, the top of the stack would be an address that is on the lower end, right? And the bottom of the stack here would be on the higher end. So the memory address of, let's say, this blue ring would be lower than that of the green ring, lower than that of the yellow ring, higher than that of the yellow ring, and this would be the lowest memory address. So that's what high to low kind of means. And this is because the stack grows downwards. And basically what this means is that in the memory layout, whenever the stack is gonna expand, right, it will expand on the lower memory address end. So usually normal regions, they're gonna expand at the higher memory address, right? But the stack is not the opposite. So like this, when we want to add data over here, we're gonna be going from here and then downwards and downwards, and this is towards the top of the stack. Okay. Now another thing that we need to understand is how machine instructions actually work, right? And this is called assembly. So what assembly is that it's kind of a layer of abstraction before the actual like bytes that represent the instructions in a program. Basically, the assembly is kind of like if we were to convert the machine code to a human readable version of the instructions, right? So for example, in the executable or the binary file, right, you might see these bytes and they're going to represent certain instructions, right? So assembly is the human readable version of these bytes, which you can see here is like a move instruction and some registers. But the reason why assembly is important is because it is part of the process of how we compile programs, right? For example, in the C programming language, when we write some code, it's gonna be in this human readable form, right? So this is at the top layer of the the code writing process. Now, when I compile it, it's gonna be translated into the actual machine code, right, or the actual bytes. And if we want to uh, read exactly what each machine instruction is doing, we have to represent them as a assembly because it's more human readable. Now, one thing that you might kind of heard of is that assembly is this very scary, very verbose form of code that people don't usually write anymore, and that's correct. So you may be asking, if that's true, why is it so important that we understand assembly? Well, if you remember, binary exploitation is about exploiting the certain vulnerabilities in the memory, right? And to do that, we must be able to understand exactly what goes on at the machine code level so that we can exactly pinpoint what's actually vulnerable in the memory level, so that we may be able to exploit it. Yeah. Now, another thing about assembly is that instead of having what you and I call variables in human readable code, assembly doesn't actually have that. Instead, it has what's called registers, which are just like small storage areas for data when the machine is gonna do certain calculations, right? So you can kind of think of them as like small boxes, and or you can think of them as like variables, right? But instead of having as many variables as you want, let's say you only had a select few of these variables, right? A fixed amount of, if you will. Then we will have to use these variables differently in order to store and manipulate data in our assembly code, right? Some common registers that we use in assembly would be this list. However, the important ones that we will be covering more so today would be the instruction pointer, which is how the computer knows which instruction to execute. The stack pointer, which points to the top of the stack frame, right? Which is basically like the address of the top of the stack frame. And also the base pointer, which points to the bottom of what we call the stack frame, right? So these are the important registers for now. And while it may seem like a very kind of complex syntax, the majority of all programs are actually made up of 10 or so like common instructions. So whenever you see an instruction that you don't quite get, you can just consult your search engine, right? Basically, you can just Google it. So the way a certain instruction is written, right, it consists of this syntax. You're gonna have your operand, your operation, right? In this case, it's a move operation. You're gonna have some kind of destination, which is in this case a register. And you're gonna have some source. In this case, it could be a register or it could just be a value. Right. The first common instruction that we're gonna look at and we just saw is gonna be the move instruction. And what this does is basically to set the value of this uh, register over here, the REX register, to whatever value is from the source. So if let's say this was the value is 0, uh, after this instruction is executed, RX is going to be 0, right? But if let's say this was another register, like RDX, then after this move instruction is executed, the RDX register is going to be the same value as the RDX register. Another kind of common instruction is a jump instruction. So what this does is that it sets the instruction pointer to the specified address. Now what this means is that let's say you have a program over here. I'm gonna make a bunch of instructions and some like registers. Let's say this is a program. And let's say the address of this is like hex 10, 11, hex 12, and hex 13. Let's say this is the jump instruction, right? When you're executing the program, first the computer is gonna start here, right? So RIP is gonna be the RIP register or the instruction pointer is gonna be pointing to this hex 10 address, right? After it's executed this, then it's gonna move on over here, and then after it executes this instruction, it's gonna move on to the next one, and so on and so on. So now, when we arrive at our jump instruction, first thing it's gonna do So it's gonna see that the value of the operand is hex 10. And if you remember what jump does, it sets the instruction pointer to the specified address. So the address over here that we're talking about is hex 10. So after this runs, now RIP is gonna be hex 10, and it's gonna go back here. So after this, the program is gonna run as per usual. It's gonna start from hex 10. It's gonna execute this instruction, and so on, and so on. So that's what jump does. Now another common instruction is the stack operation, push and pop. Yeah, push and pop. Now, before we dive into the actual memory-specific way this works, uh, the way to visualize this is again with the visual example of the stack. Right? If you remember, the push instruction is gonna want to put the item at the top of the stack, right? So if let's say the stack was empty like this one, the stack pointer is gonna point to the bottom over here, but it's the top because the stack is empty. So once we push this blue ring, the the stack pointer is gonna be pointing to the blue ring, right? And once we push the green ring, the stack pointer is gonna be pointing to this green ring, right? And so on and so on and so on, and the stack pointer will be pointing to this red ring. Now the pop operation does the opposite of push, right? It's gonna take this red ring, take it out of the stack, and then it's gonna move the stack pointer down, right? And so on and so on and so on. So when we think of the push and pop instructions, it's gonna be exactly like that, right? If we go back to a program example, say I do a bunch of push, right? Let's say the program is gonna start at this push instruction. So now over here, let's say that the stack is empty, right? So the stack pointer is gonna be pointing here. Now, after the program, the computer executes this instruction is going to push 1. So, and then the stack pointer is incremented, right? So now this is the top of the stack. And after we go on to the next instruction and we push 2, right? Again, it's going to want to push the 2 onto the top of the stack and RSP will be pointing to it, right? Now, when we move on to the next instruction here, and you can see that it's a pop instruction, right? You'll see that instead of just a pop, it's gonna be pop some register, right? Now what this means is that other than just taking off this at the top of the stack, right? What it's gonna do is it's gonna take what was previously at the top of the stack. It's gonna set the register to that value, right? And if we go to the next instruction, you can see the same thing happening. Okay, so that's what push and pop basically do. But another thing that we have to note is that if you remember, RSP or the stack pointer is actually a register, right? And what this means is that it actually contains the address pertaining to the top of the stack. So when you remember, we were like moving down the stack here, and RSP was pointing here. What this means is that let's say the stack, the address over here is this number, and this is the next slot in the stack, right? In the computer for the stack, each slot is gonna be 8 bytes, right? So this is gonna be an 8-byte value, this is gonna be an 8-byte value. But when we say that the stack pointer is pointing to this part of the stack, we're actually saying that the value of the register is this address, right? And when we pop from the stack, what it's gonna do, we said it's gonna move the stack pointer down, but what it's actually doing is that it's gonna increment the stack pointer, right? Because the stack grows from higher to lower address, and since we're going down in the stack language, that's basically adding 8 to the stack pointer address. Right. So this is the distinction that you have to have for the machine stack and a physical stack. Right. Yeah, so like in this visualization, you can see that the top of the stack is this lower address, bottom is this hex, this higher address. Right, and as we push the items, you can see that it's going from a higher address to a lower address. Right? And similarly for the pop instruction, it's gonna go from hex E8 to hex F0 and so on. Now, if we look back to our memory layout, you remember that actually the stack is also this memory region in the computer. Right? So it's this one long, what we say contiguous, meaning the addresses are next to each other, right? So you have like address 1, 2, 3, 4, 5, all the way to some number, right? We say that the stack is a contiguous part, kind of memory. So it would be nice if we were gonna store the function context on the stack, right? And we can segment like specific areas of the stack for each specific function call. Now, the way in which we do this is called a stack frame, right? So similarly to how we can index bytes in a program by specifying sessions, we can specify the region of the stack or the address at which of the stack we are working with, right? So uh, we touched on the stack pointer, but we haven't touched on the base pointer, right? So in the stack, when you have base pointer, uh, what what you usually notice is that what this means is that this is the frame, a stack frame, right? And exactly what this means is that when we have a kind of function, say this is some function hello, right? And hello is gonna have a specific part of the stack dedicated to its local variables, its return address, something that we will touch on later, that is also stored in the stack. Right? And the base pointer basically denotes the lower end of this the stack, which is in the stack language, of course, the higher memory address. And the stack pointer will be pointing to a lower end or the top of the stack for this function context, right? And as we call more functions, right, the stack frames are gonna pile on top of each other in the stack. So if let's say we go back to this hello function and we call something like call main, right? So this is the stack frame for hello. What's gonna happen is that when we call main, and main has its own function context, the stack frame for main is gonna be allocated just above the stack frame for hello, like so. And it's gonna pile on like this as you call more and more functions. And that brings us to another common instruction, which is the call instruction. And what it does is that uh, by by jumping by jumping to an address where another function is located, it interrupts the control flow of the program, right? And other than just a jump, what it basically does is like a push instruction, but for the instruction pointer. And what that basically means is that let's say there was some function that did call hello, right? Well, the first thing the function is gonna wanna the program is gonna wanna do is it's gonna wanna know how to return to this function when we finish uh, going through this hello function, right? Let's say the instruction here is hexf1, the address I mean. So what it's gonna do is that it's gonna save this address over here, right? The way it does this is that it pushes it onto the stack. So over here, it's gonna push like say the uh, return address, which is in this case hexf1, right? Like so. And this is gonna be the return address that is popped from the stack when we exit the hello function, right? So when the function is gonna exit, it calls this other instruction ret, which is basically a pop RIP, right? And to kind of visualize this, remember when I said that this stack frame is kind of like a part of the stack that's allocated just for this program. Well, because the program itself has its own variables and it pushes its own things, right? All the actual stuff it pushes is gonna be from this to this, right? And as it exits the program, it's gonna do some kind of cleanup. So RSP is gonna be popping all the stuff back. It's gonna decrement over here until it reaches the base of the stack frame, right? And it goes to the base pointer over here and pops that too. Well, another thing it's gonna do is it's gonna pop the return address from here, right? And what it's gonna do, it's gonna pop it into the instruction pointer, and that's how the program knows it can return to this part of the function after it called hello. Okay, so basically, we can see this often in assembly. When we call a function and we exit from a function, we can see call and ret working together. Uh, because we know that call does a jump and a push, and also ret does a pop. The fact that we have separate instructions for those sequences um, lets us abstract away like the exact assembly or the push and pop that we have to do, right? Um, and that lets us have this kind of abstraction that uh, allows us to easily call programs as we like and return from them, uh, so we can have a better like mental model. And to kind of demonstrate this in assembly, uh, you're gonna wanna download this distribution from the CTA website over here. I have it with me, and you can see that we have this call and ret binary, right? You can see that the call and ret binary is a elf, which is basically the executable file, right? And to kind of see what it's doing inside, there's this program that I like to use called GDB. And what that does is basically, if you run this command, there's going to be this kind of terminal-ish interface. So you're going to open this file with this command gdb :ret, right? And some basic commands. First, if we want to run the binary, like on its own, like as we would in a normal terminal, right? Just going to run. You can also do R for short, that does the same thing. But if we want to be able to step through like each instruction specifically, this won't be so useful, right? Instead, we're gonna set a breakpoint. So what this means is that we're gonna set a point in the instructions or the program that's gonna suspend the program for us so that we can run certain commands that allow us to step through the function instruction by instruction and also examine the computer state, right? The way we do this, we're gonna see what functions there are with this command over here, info and functions, right? This is gonna give us a bunch. Okay, right, it's there because I just ran it, but if I run this again, you're gonna see that we have the function hello that we wrote, and also a main function. Now, what I want to do is I'm gonna break at the start of the main function, right? You can do this with break and then whatever function it is. It's gonna set us a break. Now, when we run the binary, it's gonna pause at exactly the beginning of this main function. You can see here, it's gonna run this instruction over here, but it pauses for us. Now, one thing that I'd like to do is I'd like to use next instruction, right, or NI for short, to step through like each instruction individually. So over here, what I want to do is I want to step through each instruction until we reach this hello call, right? So I'm gonna do that. Uh, so we're at this puts call, right? I'm gonna press enter again, right? Until and enter basically repeats the previous instruction that was ran. I mean, the previous command that was ran, right? And over here, we find ourselves at the main instruction, right? Now over here, I'm gonna want you to note this specific this address, right? Because it's the instruction after our call instruction, right? Uh, you can do this by just examining the address of your current instruction. Uh, you do this by this x/I command, and what that does is that it prints the instruction at this address, right? And if I press it again, it's gonna print the next instruction. So you're gonna want to save this address, right? 401171, and there's a very specific reason why I want you to take this address. To view like the stack from the top to the bottom, one thing we can do is we can do a telescope, right? And this basically shows you like a list of the data from the address that is specified. In this case, I use the register RSP. You can see from top to bottom, we have all these things on the stack, right? This is going to be the top of the stack. So as we go down, you can see that the address is increasing, right, as we go down the stack. And somewhere down here is going to be the bottom of the stack, right? So this command will come in use later because first I'm going to step into this call instruction, right? How we can do that is by using the step I instruction, or SI for short. If you do that, you can see that we go into this hello function over here, right? And remember when I said that the call instruction is basically a push and then a jump, right? Well, now that we're already inside the function, we just executed the call instruction. We can see what is at the top of the stack, and the way I do this is with the telescope command, and you can indicate the stack pointer register with this dollar sign and then the name of the register. If I press this, you can see that now the top of the stack that the stack pointer is pointing to, right? This address. Here you can see that it's our return address, which was the address of the instruction after our call instruction, right? This is the D1 that I told you to note, right? So now I'm gonna step through this whole function until we go to our ret, right? And you can see that at the ret instruction, you recall that I said the ret was just a pop instruction pointer, right? It's just a pop, and if you look at the top of the stack again, you're gonna see that our return address is at the top of the stack. So if I do a next instruction, you're gonna see that our stack pointer has moved down, right? But what that means is that we've returned to our function, I mean our return address, because it's just been popped on the stack. So that was just to see exactly how it worked when we ran a binary and it did the call and read instructions. But yeah, okay. Another common instruction also is a nope instruction. It does nothing. I can show it to you guys over here. Oh yeah, to see the assembly inside an instruction, you can do disassemble or just this S for main for short. I can just disas main. And if I just as hello, you can see that there's a nope instruction. And this just does nothing. Yeah. So that was it for the prerequisites. Um, and after this, Jerome will be covering how we can exactly do exploitation in the stack. He'll be covering the certain common vulnerabilities that you'll be encountering and exactly how we can exploit this with Python. Yep.